All right, let's get started. Hello, everybody. Good afternoon, good evening, or good morning, wherever you are. So it's a pleasure to welcome our speaker today. It's Agatha Atkarskaya from the Hebrew University of Jerusalem, and she's going to tell us something about the group-like small cancellation theory for rings. Agatha, please.
Hello, everybody. Thank you very much for inviting me to give a talk. So first, I want to start with brief introduction to small cancellation theory for groups, which is well-known thing. So suppose we have a group given by generators and defining relations, then it is well known that in general case, we cannot say much about structure of such group. Even if this group is trivial or non-trivial, can be algorithmically undecidable. However, in some particular cases, when we have some good conditions on the relators, then we can learn a lot from the presentation about the structure of the group. And one of such kind of conditions are small cancellation conditions. So we consider a group given by generators and defining relations. And we suppose that all relations are cyclically reduced and the list is closed under taking of cyclic shifts and inverses. Then the idea is that different relations have small common parts. Precisely, it means the following. If we have two different relators and C is their common prefix, then C called a small piece, and the group G satisfies the condition Cm if every relator cannot be written as a product of less than m small pieces. And we're particularly interested in m not less than 7. And for example, we can guarantee such condition if length of every common prefix is strictly less than 1/6 of a relator. So this is an assumption about small interaction about different relators. And knowing this, we can learn actually a lot of things about the group. In particular, such groups are always non-trivial, but I will say in a minute about it in detail. So as I told you, in fact, small cancellation groups, we can look from two different points of view on them. The first is just to study their structure. And for example, finitely presented small cancellation groups, it's known that they are hyperbolic. So such groups, they really have very good, nice structure. But on the other hand, you can go further and consider iterated small cancellation theory. Namely, you have a group given by generators and defining relations, and you split relations into groups. So you don't assume that the whole set of relators satisfy small cancellation conditions, but these parts in which we divide our set of relators, they satisfy small cancellation conditions themselves, but also they have to satisfy small cancellation conditions, roughly speaking, like the next group should satisfy small cancellation conditions modulo the previous group of relations. And this already gives us very powerful instrument if we want to study groups with unusual properties. For example, such groups appear, such structures appear when we study the Burnside groups. And these ideas, they are the basis of solution of the Burnside problem, both by Novikov-Adyan, which is more combinatorial approach, and by Alshansky, which is more geometric approach. And also a very well-known result is constructing of Tarski monster groups, which is also based on iterated small cancellation theory. And when we thought about small cancellation theory for rings, actually, we wanted the same goals, but for rings. So first of all, we wanted some ring with a nice structure, which is easy to study, which can be described in a good cooperative way. But on the other hand, we want that it has a potential to be iterated, so we can produce interesting counterexamples and interesting rings with unusual properties. So like for groups, we have such problems to produce some counterexamples. For rings, we also have such problems. And I want to tell about, okay, I will tell about one such problem. To construct a division algebra of infinite dimensional with center with a finitely generated multiplicative group. This problem stays quite a long time already, and it is not solved. And this is our current work in progress. And actually with this problem, we started this idea of producing small constellation rings. We started to think how we can apply these ideas in the ring case, because in the ring case, actually, we meet significant difficulties because it's really different things in a group where we have only multiplication, and in a ring where we have two operations. You will see which difficulties we will meet. But first, I want to say more about studying of structure of small constellation groups, because in fact, in rings, we try to follow the same path, and more or less we succeed following the same path. So let's go in some details about the groups. For simplicity, I suppose that my group actually is a group with one relator. So I suppose that all relators are the cyclic shifts of each other. But more or less the same argument works in general case, but for simplicity, assume that. And also assume that it satisfies condition C prime 1 over S, where S is not less than 11. Then, first of all, let's consider a basic transition between equal elements in such a group. So we have a relator which is split into two parts, U and V inverse, and we take a word where this part of a relator U we find, and then of course the transition from LUR to LVR gives us the same element in a group. This actually we can define, of course, for every group, not necessarily small constellation group. However, for small constellation groups, such transitions give a powerful element to study their structure. So such transition is called a turn. So we start with this word, and we switch to a complement. So this is the final word. And particularly, we are interested in such occurrences U, which cannot be prolonged further. Namely that U, it's a maximal occurrence of a given subrelator in our word. Then if U is a maximal occurrence of a given subrelator, then the resulting word LVR doesn't have any cancellations, and this is very convenient. So of course, if two words in a group G represent the same element of a group, if and only if they are connected by a sequence of turns. And in particular, we can say that if and only if they are connected by a sequence of turns of such maximal occurrences. Okay. Oh. Now let's look how maximal occurrences of subrelators can be organized in our word U. Since we know by small cancellation condition that every common part of two relators are small pieces, this means that if we have two maximal occurrences which have some overlap, then this overlap must be a small piece. Otherwise, if this is not a small piece, then actually these two subwords of relators should glue to the single relator. But since our occurrences are maximal, this is not possible. So they have small overlaps. And the second thing which I want to notice is that, in fact, if we consider terms of maximal occurrences, there are terms of two types. One type is then on the one side, we have more or less 1/2 of the relator, and on the other side, we have more or less 1/2 of the relator. And such terms, they are very, let's say they're very nice transitions because they have small influence to neighboring maximal occurrences. Because, for example, that we have some maximal occurrence which is a neighbor of A inside our word U. Then what can happen after we make a turn? Then this occurrence probably it can either increase by a small piece or decrease by a small piece. So the neighboring occurrences, they change very little. And the second type of turns is when we have some very long part of a relator, such that its complement is a small piece. So we change something very long to something very short. And this can cause some troubles. Namely, since this is a small piece, we can have some maximal occurrence from the left and some maximal occurrence from the right. And with the use of this small piece, they merge together. So this kind of troubles, we never have them in the first case, but we can have them in the second case. And now I want to show how, using these sequences of terms, we will study the structure of this group, and in particular prove that it's always non-trivial. So first of all, we introduce measure on subwords of relators in a natural way, length of a subword over length of a relator. And notice that since a term, it comes from dividing of a given relator into two parts, it means that at least one side has measure not less than 1/2. So we take two words which are equal in our group G, and then they are connected by some sequence of terms. And we can say that they are connected by sequence of terms of occurrences of measure not less than 1/2. But probably these terms goes in different directions. So I don't say that we can go in one direction with such terms, but in different directions we can go. So I mean that if my arrow goes like that from left to right, then on the left I have occurrence of measure not less than 1/2, and on the right I have something like some complement. And so for such arrows in different direction, here it's not less than 1/2. Okay, so given two words, we have such sequence of terms, which I represented graphically as a sequence of arrows. And now looking at this sequence, we want to transform it a little bit. Namely, we want to remove patterns which look like that, like two arrows going from the given point. And how we're going to do this? Actually, this happens if I have in one word, I have two occurrences which are long enough, and I go and make shorter result in one side and on another side. So first, suppose that here I draw one particular case, which actually is the most interesting, but of course, probably these occurrences which produce this pattern, probably they don't have overlaps, or maybe they are even not neighbors. But I think that this is the most interesting case. So in upper part, you see the initial pattern, the turn of UI to U1 to V1 and the turn of U2 to V2. And the down part, it consists of the turn of U2 prime. It's a leftover of U2, and the turn of U1 prime, which is a which left from U1. And one can easily see that the result, if I turn U2 prime in this monomial, and if I turn U1 prime in this monomial, the results are equal. In a sense, I can say that on the left, I perform my turns in order 1, 2, and on the right, I perform my turns in order 2, 1. But what makes sense for us, that if at least one of U1 and U2 has measure greater than 1/2 plus 2 over S, then the length of the final word is strictly less than the length of the initial upper word. So with our sequence, when we see patterns which satisfy this condition, this and this, we do this transformation. And after doing this transformation, we look at the resulting sequence, and if in this sequence we have some turns which now violate our condition that we turn only bigger half to smaller half, then these arrows we just reverse. And then again, we repeat this transformation. And this process stops because sum of length of all words strictly decreases after each step, because with the length of this word is strictly smaller than the length of this word. So in a sense, we can say that we look at this sequence and we kind of cut peaks in this sequence. And also this transformation, this can be considered as diamond lemma. Okay. So finally, when process stops, we obtain a sequence of this form. So we removed all patterns where arrows goes outside. So we can have only patterns where arrows goes inside, and this can be only a single point. What I also need to mention, that if we have situations that both occurrences here, that we still have this pattern where arrows goes outside, but these words are not greater than 1/2 plus 2 over S, Then at the final step, we also will just reverse these arrows in order to remove a pattern which we don't want to see. And then we actually obtain sequence which looks like that. But we can say that in this sequence, we turn occurrences of measure not less than 1/2 minus 2 over S. Okay, and now it remains to say that we take two words and we take them such that they don't contain greater than 1/2 of any relator. This is always possible to do. We take an arbitrary word, and then if it has some something greater than 1/2 of the relator, we turn it. The length strictly decreases, so we continue this process, and since the length strictly decreases, the process stops. So we always can say that we take two words which doesn't contain such greater than 1/2 of a relator. And let's look at the sequence of such form, sequence of terms, which connects U1 and U2. I claim that in such sequence, we will have only terms of the first type, only terms from here of the first type. Indeed, we start with something which doesn't contain even 1/2 of the relator. Of course, the first term is of such type. Suppose this was the first term. Then after that, we look at its neighbor. Probably neighbor increases or decreases, but only by a small piece. So the next term also will be only of the first type. And also notice that having terms of the first type, it never can give us accumulation of changes of maximal occurrence. I mean, if, for example, this maximal occurrence was increased or decreased after the turn of its neighbor, this is a single change. Other turns from the same side, they never will give any further, they don't give any further influence to this occurrence. Therefore, for such words in this sequence, all terms are of the first type, and moreover, on the way, we obtain occurrences only not less than 1/2. We obtain occurrences only not greater than 1/2 plus 2 over S. This is the maximum measure which we can have. Therefore, it means that, in fact, this sequence of terms can be represented as a one-layer map where every region represents a single term, and the words U1 and U2 are paths in this map. So this is basically the structure of every small constellation group. In particular, from here, we can say that this group always non-trivial, because one layer map corresponding to one, it's a single point. And if we take some non-empty, but less than 1/2 piece of a relator, then it's one layer map, it's a single region, which is different from one point. Therefore, such word and one don't belong to the same one layer map. Therefore, they are different in this group. So this group contains some non-trivial elements. And I told in such details about this.
So this picture down like at the bottom of the page. So this is a picture of two geodesics between 2 points. right?
Actually, I don't consider them as geodesics. Actually, I just want to say that this picture shows transition from U1 to U2. So
and
if I have two,
is like one layer. So basically one layer in terms of one layer of regions.
yes, exactly.
Olga, I think here the assumption is that U1 and U2 are then reduced. They don't contain more than one half of a relator each. And that's the structure of the equality.
Yeah, no, I understand. Yes, but I mean, okay, so this is basically right. So this is just a word and it's not a geodesic word.
Yeah. I don't claim that this is a geodesic word at all.
Okay.
Okay, so I told about this argument in such a detail because basically we want to follow the same argument and to model the same situation when we speak about small cancellation rings. So let's now move to the ring case. As I told, we started to think about such rings from this problem, how to construct a division algebra of infinite dimension over its center with finitely generated multiplicative group. And this problem is not solved yet. We're still working on it, but the idea is as follows. We enumerate all monomials in a free group. So we take a free group, we take its group algebra. For simplicity, we take it over the 2. So we enumerate all monomials and we take ideal, which looks like that. Every binomial 1 plus wi is equal to some vi inverse, where vi inverse we choose in a clever way. Namely, we choose them in such a way that they exhibit some kind of small cancellation properties. Then, if it happens, if such good fortune happens that the quotient ring is non-trivial, then this is exactly what we need, because in the quotient ring, every element is either 0 or is a monomial, so is invertible. Therefore, this final quotient ring is a division algebra, and after that, it's possible to show that it has infinite dimension over its center. So then the first step is this ring, where we equate a single binomial to a monomial. And we started.
I have a question. So
yeah.
who are these W1, WK? So are
these are all elements, these are all elements
all
of free groups. Yeah, all monomials. Actually, we take all primitive monomials, which are not proper powers. It's also enough.
Okay.
Okay, and so the first step is to study ring where we equate one binomial to a word. And this is actually a ring which gives an origin of our small cancellation theory for rings, because we started to study its properties and we realized that in fact we don't use that much particular form of these relators. So in fact, we just use some list of properties which can be stated as list of axioms. And the first question, when we look at a ring given by generators and defining relations, is how to define small pieces. When we study this ring from which we started, I need to notice that it doesn't matter which field we take. So K is just some field. So when we study this ring, then we take V, the word of this form, where alpha and beta are constants, which guarantees us long enough word. And the word is of the form x alpha y, x alpha plus 1 y, etc. Then these words exhibit small cancellation properties, because if we take a subword which which contain two letters, at least two letters y, then it has a fixed position in a V. So if we take such a relator as a group relator and consider a group with such a relator, then this is a small cancellation group. And also, in order to study such quotient ring, we need to extend in a clever way our set of relations. Considering only this is not enough. Namely, we take all Laurent polynomials over V and W such that we can deduce them from this polynomial, from this equality. And also we add all their shifts. Like in group, we add all cyclic shifts, and here we just add all their shifts. And of course, if we look at these relators of this particular form, then it's very natural to say that very good candidates to be small pieces are exactly like group small pieces, namely subwords of V of a form X in some power gamma or X in some power gamma Y. So the words which contain less than 2 letters Y, or if we consider V inverse, less than 2 letters Y inverse. And but the question is how to extract information about small pieces if we just look at the list of relators. I mean, here the relator, it looks very clear, and we choose these particular words to be a word with small cancellation properties. So of course it's natural to say, okay, we take small pieces from a word with small cancellation properties. But what to do in a general case? However, this particular case, it gives a nice suggestion what to do in a general case. Namely, compare the following relations. This one, V plus VW minus 1. This one, V square W minus V. It's both from the list of relations for this ring. And let's take a shift of this relator, namely assume that V we separate into 3 parts. Some initial part VI, middle part VM, and final part VF. And I want to take a shift by VI inverse. So the relation VM VF, VM VF W minus VI inverse. Then if we look at them, I want to say that in the group case, we just look at different relations and look at their common parts, so at their common prefixes. Here we cannot do like that. We cannot take just 2 different polynomials and look at some common prefixes, because in fact polynomials, they can be grouped into some sets which are similar. Namely, if we look at these 3, for example, relations, then these 2, they are similar. They are not good to produce small pieces. Namely, both of them still are in the set of relators if we multiply them, for example, both by V or both by W, or both by any monomial in VW. On the other hand, for example, if I take this relator and this relator, they are not similar in this sense. Namely, I multiply this by W and I stay in the list of relators. I multiply this by W and I don't stay in the list of relators. Or I multiply this by VI and I stay in the list of relators. I multiply this by VI and I don't stay in the list of relators. So such pairs like this and this, they are good to produce small piece. And this explains the following definition of small pieces in ring case. So our general setup is the following. We have a group algebra. We have a set of elements, and we require that it's closed under taking shifts, namely, if I have some polynomial from here and x inverse is a prefix of some monomial, then I require that multiplying by this letter x keeps us in the list of relators, and the same from the right side. And we take an ideal generated by the list of relators R as an ideal, and we study the quotient ring. And so for this setup, we define small pieces as follows. So assume that M is the set of all monomials from the relators, and consider two polynomials from the list of relators, P and Q, and let P has a monomial which contains a subword C, and let Q has a monomial which contains a subword C. Then we say that C is a small piece if we consider P, we cancel here A1, and instead of A1, put B1 like here, and do the same from the left side, cancel A2 and add B2 from here. And if at least one of these polynomials doesn't belong to our list of relators, then C is a small piece. So as I told here, we speak about small pieces in a sense of prolongations of relators. So small pieces, they don't fix prolongation of relator, and non-small pieces, they fix all prolongations of relators. And we need to require separately, just by hands, that the empty word one is always a small piece. Okay, having a definition of a small piece, we can formulate small cancellation condition. Small cancellation condition looks as follows. Assume that we have a number of polynomials, and we take the linear combination, which is non-zero often after additive cancellations. Then we require that in every such linear combination, we have a long enough monomial. Long enough in a sense that it can be represented as a product of at least 11 small pieces, or it cannot be at all represented as a product of small pieces. Here we have small difference with the group case. For groups, it was enough to require that only every single relator is long enough. Here we have to take linear combinations, but this is unavoidable. I mean, if I take some linear combination of polynomials from the list of relators and obtain the result where all monomials are very short, then no chances that any small cancellation ideas will work, because the idea why small cancellation conditions work is that if I have some dependence between words, then this dependence has a big fingerprint if at least one word. So that's why we need here unavoidably to use linear combinations. And also, in order to define small cancellation ring, we need a third condition, which is called isolation condition, but I don't want to speak about it in detail. It's about, roughly speaking, it's about that monomials which have very small difference in terms of small pieces, they cannot participate in the same polynomial. Okay, so now after we defined a small cancellation ring, let me show how these conditions work. And how we follow this argument from groups in our ring case. First of all, instead of turns, we now have multi-turns. So there in groups we had part of relator and its complement. Here now we have a linear combination, and we go from one monomial in this linear combination to a sum with the inverse, with minus sign, of the remaining monomials. Here I have a misprint. I mean that I have LUI0R goes to this linear combination of LUIR. So here I mean LUIR. And such a transition is called multi-turn. And again, we consider multi-turns of maximal occurrences of elements from monomials of relators, which are long enough. Here we need some tricky definition for these occurrences, which we actually consider, but intuitively, you just can imagine that they contain at least 8 small pieces. And the same 2 elements of our group algebra are equal in the quotient ring if and only if they are connected by a sequence of such multi-turns. So now imagine 2 elements of the group algebra. They are connected by a sequence of multi-turns. Now, again, we want to remove this pattern with arrows going outside. So we want to cut peaks. But here it's not possible to do in such a direct way, but I'll show you a general idea. So first of all, consider such a pattern. So we have a single monomial. We have 2 occurrences of our monomials from relators. And for simplicity here, I assume that they are separated from each other, that they are not neighbors. And assume I turn U and I go here, and turn V and go here. And suppose that we have some good measure on monomials. And with respect to this measure, here all monomials has smaller measure than the initial monomial, and here all monomials has smaller measure than initial monomials. Then we can do the same trick as in groups, namely in this monomial we perform multi-turn of V, but now we need to do it in every monomial. And here we perform a multi-turn of U, again in every monomial. Then the result in both cases is the same, and it's equal to this polynomial. So if everything is good and measure everywhere decreases, then we can argue in the same way as in groups, in fact. However, I show you a kind of ideal case. First of all, the problem is that here in different monomials, we can have different effects. Namely, for example, in some monomials, we can have cancellations. So it's unclear how to do the next turn. Also, it can be that in some monomials in the result measure decreases, in some monomial in the result measure doesn't decrease. However, even this naive example shows the main idea. It suggests us how we should formulate diamond lemma in our ring case. Namely, let's consider in detail how we go from this monomial with the upper path to this monomial and with lower path. Of course, having a multi-turn it's in fact when we add to this monomial the corresponding linear combination, which is produced from here, LPR. So going here in the upper path, it can be represented as we start from this left monomial. We add linear combination corresponds to the first term, which returns us to LUMVR. And then we add a linear combination, which leads us to the right side, which is this. Okay, let's look at these two expressions. We can cancel this monomial from them, the initial one. Okay, but now we need to switch to a down path. In order to do this, we add and subtract Q. This always we can do. However, now if we look at this expression and at this expression, they are linear combination of some expressions which correspond to multi-term. Namely, here we exactly have linear expression which correspond to multi-term of U in every monomial, and here which correspond to multi-term of V in every monomial. And this simple calculation explains us why the next statement, which is the main statement which helps to study small cancellation rings, why it can be called diamond lemma. Okay, so first of all, let's formally define these expressions which correspond to terms. Namely, we consider polynomials of the form alpha LAIR such that this corresponding sum alpha IAI is from the list of relators. We consider the linear span. Here, this angle brackets means linear span, not an ideal. And these linear generators are called dependencies. These are kind of standard dependencies for us. And notice that by small cancellation condition, in a given dependence, always there exists a monomial with long enough AI, namely with AI which contains at least 11 small pieces. And as I told, we suppose that we have a measure on our monomials. This is a separate story how to introduce this measure. I don't want to touch it now, but suppose that we have it already and it's good enough and it catches the idea that if we replace something more or less long to more or less long, then it keeps the same. And if I replace something very long to very short, then it decreases. So suppose we have such measure. Then with respect to this measure, we introduce a filtration on our group algebra, and we define dependencies for each level of filtration. So this is a linear span of standard dependencies, but not all, but only standard dependencies which are contained in the nth level of the filtration. Then the diamond lemma states that if we take linear combination of dependencies from the nth level of filtration, and it happens that it goes down to the previous level, then in fact it belongs to linear combination of dependencies of the previous level. So roughly speaking, it means that if some long occurrence, if some long monomials cancels in a linear combination of dependencies of nth level, then in fact we actually don't need them. We can generate it as a linear combination of dependencies only from the smaller level. And this little calculation, it expresses exactly this idea. This monomial, it was a lone monomial, and it cancels. But we see that instead of this single lone monomial, I can add many smaller monomials and still obtain a linear combination of standard dependencies. That's why it's reasonable to call this statement diamond lemma for rings. Although it looks completely different, but it keeps the same idea and the same spirit. And this is very convenient thing to work with in the ring case, much more convenient than classic diamond lemma. And from this statement, we already can extract all information which we need. For example, using this statement, we can show that our ring is always non-trivial. So let us take some word from the zero level of filtration. Zero level is always non-empty. And assume that it's equal to 0 in our quotient ring. Then it means that there exists a linear combination of standard dependencies, that U plus this linear combination is equal to 0. And of course, this linear combination, since it's a finite linear combination, it defines some to some level n. However, since we have this equality, from diamond lemma, we obtain that this T, it must belong to dependencies of the 0 level. Because as a result, we obtain something from the 0 level, which means that monomials of upper levels, they just cancel out. But if they cancel out, we go down to linear combination of dependencies of smaller level. And now for us, final small level is 0. However, at the 0 level, we don't have any dependencies because of this small cancellation condition. And our measure, it catches this, that if we have some long occurrence of a monomial of a relator, then it is non-zero. So such subword with a long occurrence, it is never on 0 level. So small cancellation condition implies that dependencies of 0 level, it's just empty set. So a contradiction, we cannot have such equality. In particular, 1 is always at 0 level of filtration. So at least we always have that 1 is not equal to 0, which is enough to claim that the ring is non-trivial. And that's all about structure of our rings. But I want to say a little bit about further work. Namely, it is known that small cancellation groups are non-amenable. I don't want to speak much now about amenability, but the group, or here I have a misprint, the group G is amenable if it admits a finitely additive measure such that it's invariant under translations. And it's known that if a countable group G contains the free group with 2 generators, then G is non-amenable. And for small cancellation groups which satisfy condition C prime 1/6, it is known, it is proved that they contain a free group. So because of this, they are non-amenable. And we are interested in a question whether small cancellation rings are non-amenable. There exists a definition of amenability for K algebras. It's given by Gromov and Bartoldi. And you see here a definition. And what I can say about this definition, from this definition, we can show, for example, that a free associative algebra is non-amenable, and that the group algebra of a free group is also non-amenable. And the question is whether our ring is amenable or not. Different people ask us this question. So Gromov asked us this question. And now what I'm able to say, recently I proved that under some small natural restrictions, a small cancellation ring contains the free associative algebra with two generators. Unfortunately, it's not enough to say that it's not non-amenable. It's not like in groups. However, this is some step towards to proving of non-amenability, and our conjecture is that small cancellation rings, at least under some natural small restrictions, are non-amenable. But this is not proved yet. This is also the work in progress.
But wait a minute, but free associative algebra, let's say in two generators itself, it is non-amenable.
Yes, it is non-amenable.
But okay, so but it can be amenable and contain it.
Yeah, the idea is that we don't know how this free associative algebra is contained inside our ring, and it matters for non-amenability of the whole ring.
Okay.
And I stop here. Thank you for your attention.
All right, thank you very much. Let's thank Agatha for very interesting talks. Thank you.
Yeah.
So now, if there are any questions, you're welcome to ask them to the speaker.
I have a question. It's Alexei. So your theory of this small constellation, so if you have a small constellation ring, I guess the membership problem to say ideals, is it decidable or not?
I need to say that we studied not a membership problem to an ideal, or do you mean that if I have an ideal which satisfies the small cancellation properties, membership to this ideal?
No, what basically I'm aiming to, can you, your theory, can you produce something interesting basis for an ideal, like Gröbner theory produce some particular type of basis? In your case,
Yes, I see what you mean. Yes, we can produce a good basis. And as you told, we also noticed that it's quite similar to Gröbner basis theory and diamond lemma. You know, it says something, that it has some connections. So the ideal membership problem, or the same, I formulated it as equality to zero in our ring. It's how to say, it's like half algorithmically decidable. I mean that we have something very similar to a greedy algorithm, which we have for Gröbner basis, and it works more or less for standard dependencies. We need to take some clever extension of the standard dependencies, but basically it works for this. Basically, this is a good basis of an ideal. However, I need to say that we have quite complicated measure here, and the procedure, like if we take polynomial, we need to decrease measure of the leading monomial, and this process to find if it is possible to decrease measure of leading monomial, if there exists any polynomial which can decrease it. We don't know in general cases this is algorithmically decidable. For some particular cases, maybe it's possible to prove, but in general, no. But modulo this black box, this is algorithmically decidable.
So can I ask you, I didn't understand exactly. So it's like modular black box, it is decidable the membership problem in the small cancellation ideal, right? So
Yes, yes,
ideal.
yes.
I see.
So
But if saying, I'm sorry, Ilya, go ahead.
I had a question which I think may be a little related. So I can't remember whose theorem it is in the group small cancellation group case, but basically there is a statement which says that in a free group, if you have two small cancellation sets which have the same normal closure, or if you then those two small cancellation sets are actually the same. I was wondering if something like that is true here. That is to say, if you start with a free, I don't know, free associative algebra, and you have two sets of relations which both satisfy the sufficiently good small cancellation property, and they generate the same ideal, whether or not it, one can conclude that these are actually the same set.
I never thought about that, but my first idea that no, I don't think that it's like that in a ring sense.
Okay.
But I don't know exactly.
Alexei, you wanted to ask something?
Just quick question. So it seems, Agatha, a lot of things are kind of not hidden. You didn't tell us about the measure, but a lot of things are there, right? How you define this?
Yes. The idea is that this measure, again, roughly speaking, it's in a given monomial, it's number of long maximal occurrences. But again, the question is which long, and it's the question is in which sense long, yeah, and this is the whole process to say in which sense.
Mm-hmm. Okay, thank you.
All right. Are there any other questions? Okay, let us thank Agatha again. Thank you.
Thank you very much.
Yeah,
Eugene, did you have a question?
no, of course not. I just wanted to mention that it's quite tempting to study hyperbolic properties of small cancellation rings and maybe basing on it to guess what is the general definition of small cancellation ring, at least. But this should be definitely an example. If any exists, then it should be an example of hyperbolic ring.
What
And
is a hyperbolic ring?
I said, Oля, we don't know, but if there is a hyperbolic ring, it should be small cancellation ring as a particular example. So,
No, but I mean, you should kind of have maybe some ideas, because there are different definitions of hyperbolicity. I mean, there are different equivalent definitions of hyperbolicity for groups, right? And one of them may kind of serve better for rings than others, but which one?
yeah,
I need to say that Ilya Reeves suggested that probably we should take algorithmic properties of these rings as a basis for definition of hyperbolic ring, because there we can say again about length of this sequence which leads to zero. I mean, at least here we have some tools how to, touch our ring, how to do something with our ring.
but the impression that most of the properties valid for hyperbolic groups somehow can be translated to the notion of this ring, and this ring in the proper formulation satisfies. So that is the feeling, and at least at the moment.
Just had one comment. It's maybe not kind of directly related, but in our paper with Rizas about random groups, which is in the archive, I mean, we study a lot geodesics in small cancellation groups with C prime 1,8. And like this is like this single layer Agatha was talking about. I mean, it appears there. It's basically basically it's interesting that kind of the main property of this, or the very important property of these groups is that between 2 points, there are actually quite a few geodesics. I mean, they differ, they all belong to some kind of narrow, whatever, single layer, kind of rectangular or something like this. And in small cancellation rings, like, I mean, can it be that kind of the property that actually an element is represented by like quite a few ways? Is it like, is this happening?
Quite a few what, sorry?
Quite a few ways. I mean, that's a number of ways you can represent the same element is kind of not very like, that's not too many ways to represent the same element.
Probably you are right. Again, I didn't, haven't ever tried to think like that, but yeah, probably this will hold.
The whole problem, Oля, that we don't have a model, geometric model for ring, which can be considered like a, I don't know, like a calligraph, whatever, where we can model, we can try to investigate geometric properties of the ring. So that's why Ilya Rips just said that we're obliged to translate these properties to the combinatorial language and then to find something similar in ring case. So we don't have a geometric vision for rings. What is the model? That's the problem.
It is possible that something like an isoperimetric function or an isoperimetric inequality can be made sense of here. You know, if you have a relation, it's a linear combination of monomials. You know, so you can take something like the sum of the lengths as the sort of the length of this expression, and think about how many applications of the relations are necessary to reduce it to 0. You know, so I think that one can try to define at least the notion of area combinatorially and something like the notion of length, you know, combinatorially as well, and see whether or not it leads anywhere.
Yeah, I think exactly this is quite possible, and this exactly what Rip suggested to study this. Length of this path to 0, which is basically what you are talking about. Yeah. This is very good thing to think about.
Or it may be a variation of dense property, because your sort of technology is it fits well to the finding a dense presentation sort of. So going to hyperbolic groups not from geometric considerations, but from the reduction viewpoint.
Yeah. What I told, from the reduction viewpoint.
So it's equivalent to have a nice presentation, which is an analog of dense presentation for hyperbolic groups. And
okay.
That would be, it seems like, conceivable here.
Yeah, thank you.
Okay, any other comments? I haven't stopped recording yet, so we're still in the recording mode. Okay, if not, let me stop the recording so that if